Thank you everyone for coming. Today's speaker is Dr. LiDong Pan, and LiDong got his PhD in physics from the University of Minnesota with Ching-Cher Wang, where he worked on surface effects in liquid crystals using X-ray diffraction. And then more recently, he's moved to a postdoc position where he is now at Johns Hopkins University in the physics department with Peter Armitage. And today he's going to talk about some of the work that he's doing there related to quantum spin ice. So I will turn it over to LiDong for the talk. But first, we traditionally give our speakers gifts.
Thank you. Thank you, Randy. And thank you for the invitation. It's been a very pleasant visit despite the weather. So today I'm going to talk to you about some work we've done at Johns Hopkins. Our work at Johns Hopkins is funded by U.S. Department of Energy and the Gordon and Betty Moore Foundation. So first, I'd like to acknowledge our collaborators. The work I'm going to tell you about has been done at Peter Armitage's group in the assistance of a fellow postdoc, Chris Morris. And Saeed Kupriya is an X-ray scientist in our department who helped us orient the single crystal sample we had. And locally, we obtained some theoretical support from Professor Oleg Chernoff and his grad students. And the high-quality single crystal sample we obtained has been provided by Bruce Gillen's group at Master University. Recently, Kate Ross moved to a shared postdoc position between Johns Hopkins and NIST. So here's my outline. Today I hope to tell you a little bit about frustrated magnetism, basically try to convince it is interesting and it's worthwhile to pay attention to this system, and also tell you why we use time-domain Terahertz spectroscopy. Basically, it's a very useful technique. And also tell you what Terahertz brings to the table in the study of quantum spin systems. All right, let's start. So, conventional long-range order ferromagnetism has been known to humankind for a long time. It's documented in Greece, India, about 2,000 years ago, and has been used in China. So, traditional for localized magnetic moments, you can think of a long-range order ferromagnetic states in this kind of way. All the space points up, so you have a long-range order. And meanwhile, long-range order, the antiferromagnetic, is known to people relatively much shorter time. It is because one reason is it is much more difficult to detect something that has net zero macroscopic magnetization. For example, in an antiferromagnet, you have things pointing up and down, so they have zero net magnetic moments. And so how do we detect the existence of long-range magnetic order in experiments or conceptually? First of all, you can think of it, long-range magnetic order would be a symmetry breaking transition from a high-temperature disordered state. In high temperature, we have a power magnet where the spins point to random directions in space. As a result, you don't have a preferred direction. But when it's ferromagnetically ordered, like shown here, then the spins pick a particular direction to point in space. As a result, the rotational symmetry is broken. And another way of thinking of this is this type of long-range magnetic order has a well-defined order parameter. For this case, it's the magnetization. So if you look at the two-dimensional Ising model as a function of temperature, the black curve shows you the magnetization. If we look at the magnetization as a function of temperature, there's a well-defined temperature where it turns on. And at the same time, we can look at the other quantities that can be somewhat dynamically measured. For example, heat capacity. If we look at heat capacity, it shows a divergent behavior at exactly the same temperature where the magnetization turns on. So you know, those all goes to a well-defined phase transition point. And also the behaviors of susceptibility can also be used to define this long-range magnetic order. And another defining feature of conventional long-range order is the existence of well-defined excitation. For example, if you have a crystal lattice, then we know phonons exist. You hit it, then the lattice will vibrate. The same thing happens for large magnetic ordered crystals. For example, you can have well-defined spin wave, or we can say magnons exist as excitations. So they have well-defined energy and momentum relation we call a dispersion relation. This shows you the dispersion of the spin wave in a particular material as a function of the momentum. So this brings us to a question: is it possible to define a new state of matter without symmetry breaking? And to answer that, let's take a look at what is frustration. So if you Google it, you'll find that frustration means the feeling of being upset or annoyed, especially because of inability to change or achieve something. So why is there frustration in spin systems? There are actually many reasons, many different ways of frustration in spin systems. Let's take a look at a particular way called the geometrical frustration, where frustration is brought in by a special lattice geometry. Here, suppose we have a triangle lattice, and we have the nearest neighbor interaction between the spins, and the spin interactions of the antiferromagnetic type. So if you have one spin points up, then every spin prefers to point down. If we put two spins here, then this spin will point up and this spin will point down. Then what about the spins here? It turns out, no matter how you point it, this spin would be unhappy to one of its neighbors. For example, if we point it up, then this bond highlighted in red, this would be in a higher energy state because it cannot be in antiferromagnetic order with this one. So as a result, this bond is unhappy and costly, so this is frustrated. And the frustration in magnetic system would lead to ground state degeneracy. For example, for this state, if you flip all the spins by 180 degrees, then the total energy of this triangle is the same. And also we have a unhappy bond here, but in a triangle we have three sides. So the unhappy bond can exist either on this side or on any of the two other sides. And they would cost the same amount of energy. So as a result, we have a ground state degeneracy, which is huge. And because of the ground state degeneracy, the spins can fluctuate down to very low temperature among these degenerate states. And this is a typical sign of having frustration in a system. And instead of classical Ising type of spin, if we bring in a more quantum mechanical spin, for example, spin 1/2 into the system, and instead of Ising nearest neighbor Ising type of spin, if we have Heisenberg type of spin, which is isotropic in space, then it is possible to have these spin singlets forming at nearest neighbor pairs. So here, instead of spin points up and another spin points down, the spins on the nearest neighboring sides can form a singlet, where it's a superposition of up-down and down-up configuration. And when this happens, we can have either this well-formed lattice order spin singlet size, or we can have a more exotic order, which is called the resonant valence bound, where the state is actually a superposition of all possible ways of mapping the lattice with these singlet states. So the way to think of this is a single state, which is in fact a superposition of all possible realization. And for this picture, I showed you the realization of resonant valence bound states, where singlet is paired by nearest neighbors, and it's also possible for the singlets to form when spins are located by at more distant sites. And going back to the previous question, is it possible to define new state of matter without symmetry breaking? So if we take a look at this state, actually this state has a lower symmetry compared with the lattice. So this is a symmetry broken state. Those two, because it's a superposition of all possible configurations, so the symmetry is actually the same as the lattice symmetry. As a result, those two states, although they are different states from the high temperature disorder state, it is a different state of matter. And if we look at those two states, They are not product states of any kind, but the valence-bound solid state can be defined as a product state. And there's no symmetry breaking, there's no conventional long-range order in valence-bound states, and there's no classical analog of the valence-bound states. It's a purely quantum mechanical object. So this is quite interesting. And if you want to define the turning out of this type of states, you cannot actually define by any macroscopic thermodynamic measurement. So you won't find this type of signature if you look at this type of materials. So another feature is in this type of material, it is possible to have long-range entanglements and no type of excitations. So what do I mean by no type of excitation? For a resonance valence-bound state, if there is a single spin that's not bounded, it behaves as a spin-out, which means on this side, this object will carry a spin 1/2 moment, but it does not carry any charge. So as a result, it is realization of a fractional excitation in the quantum spin liquid. So this is the normal excitation that I refer to here. So where do we look for quantum spin liquid systems? The general rule of thumb is if we bring geometrical frustration, then it's possible to realize the quantum spin liquid. And also to maximize the quantum fluctuation effect, we want small spins, and also we would want to have small spin-spin interruptions. And this brings us to the use of Terahertz spectroscopy. So if we look at the electromagnetic spectrum, it's very, very wide, and it covers all energy range. And if we want to study some material, then basically we want to pick a spectral range that's relevant to the material that we want to study. And as I mentioned, for the quantum spin systems, the energy range is usually defined by the interaction, which here I write as J. And if we look at the electromagnetic spectrum, we realize 1 terahertz has a wavelength about 300 micron and has an energy about 4 milli-electron volts. In terms of temperature, it's about 48 Kelvin. So it's relatively in the range of the spin-spin interaction in those systems. This is why we pick this spectral range to look at our materials. So we all know that if we want to know the exact nature of a material, it is a good idea to probe this material at its natural frequency. For example, if you look at the resonant frequency of a mass spring system, then you learn something about mass and spring constant. And if you know the material properties of tuning forks, and the frequency, the natural frequency of this tuning fork system is solely determined by the geometrical shape. So what I'm trying to say here is knowing information about the natural resonance frequency would already give you some information about the system. So probing a system around its natural resonance frequency range is a good idea in studying these materials. And here I show you a typical time domain Terahertz spectroscopy setup. So here we would have a femtosecond laser pulse coming that gets splitted at the beam split. One pulse gets directed here, another pulse goes through a delay stage and hits on this we call emitter. This is a zoom-in view of the emitter. It's just a dipole switch. Here we have gold. It's usually deposited on low temperature gallium arsenide. And when the femtosecond laser pulse hits it, it creates photocurrent. And then the photocurrent, the oscillating photocurrent, would act as a dipole. As a result, it emits a Terahertz pulse, which travels down this path. It goes through our sample and then gets directed to the detector. And another pulse we split here would hit the detector at the same time. The length of those two pulses are shown here are not up to scale. This pulse, the Terahertz pulse, is usually a picosecond long pulse, but this is usually a couple of tens or hundreds of femtoseconds. So if you think about it, this pulse is really much shorter than the Terahertz pulse. So by changing the delay stage, we can tune when this pulse hits the detector we can tune when this pulse hits the detector at a specific time when this pulse hits it. So as a result, we can use this pulse to chop off this terahertz pulse or measure this terahertz pulse. So here I'll show you a typical scan. Here is a typical terahertz pulse without sample. So by varying the delay stage position, we can map out the electric field of the terahertz pulse as a function of delay stage time. So actually what we measure here is the photon current, and it's directly proportional to the magnitude of the terahertz pulse as a function of its position in space. And if we take an FFT of this pulse, we can transform it into frequency space. So this is the frequency amplitude of this pulse. So you can see we can get reasonably well terahertz frequency range from about 0.1 terahertz up to usually 2.5 terahertz. And when we're putting a sample, because sample is usually optically thick, so the pulse needs to travel more distance. As a result, the terahertz pulse would be detected at a later time. And if we take the FFT of the pulse, we get this red curve here. And usually, the FFT of those two pulses are a complex spectrum. And here I just showed you the magnitude of the pulses. And the ratio of these two pulses, the ratio of the FFT of those two pulses will give us a complex transmission function from which we can obtain the complex conductivity or other similar related material parameters. So in the study of quantum spin liquids, usually there are a couple of obstacles. From a material point of view, the one obstacle comes from the disorder and defect of those materials. When you have even a small amount of disorder, the perfect balance that comes from the geometrical frustration is disrupted. So as a result, at low temperature, instead of having a quantum spin liquid, the material can go into a spin glass state, or it can freeze, or sometimes it can have conventional long-range order state if you have disorder or defect. And in order to avoid this type of effect, our colleagues in the chemistry department proposed a very interesting idea. Here they synthesized the material called lithium zinc molybdenum oxide. Instead of having a spin moment on a localized ion, they distribute a spin moment across a cluster of 3 molybdenum ions. And this way, some of the disorder effects can be avoided. And if you do a simple electron count, you would realize that over a single triangular cluster, there are a total of 7 electrons. And 6 of them would be distributed along this triangle in the metal bonds. And so as a result, there's only one single electron shared by a cluster. So each cluster actually behaves like a spin 1/2 particle, and as you look at the magnetic plane, which is here, these clusters form a triangular lattice. So if you think about it, it's a triangle of triangle. And this way, some of the disorder and defect effects can be minimized. And when we measured thermodynamic quantities, we find that this material does not show magnetic order down to very low temperature, 70 millikelvin in this case, although it shows a pretty big Curie-wise temperature. So the spin-spin interaction is strong. And if you look at the inverse stability, there is a kink at about 100 Kelvin. And looking at the filling coefficient, people realize that this material shows this interesting property at high temperature. All the spins are in a paramagnetic state, but as you cool down to below 100 Kelvin, it looks like 2/3 of the spin disappear. You're only left with 1/3 of the spin still in a paramagnetic state. And what people believe is happening is that 2/3 of the spin actually condensed into a valence bound state. And it's not a static state, it's a dynamic valence bound state. So this puts this material as a good candidate for the quantum spin liquid state. So what can we do with Terahertz to study this material? We perform the Terahertz electron spin resonance on the spin cluster material. So let me tell you a little bit about what is ESR. If you think about a spin, and then you put a spin in the magnetic field, then you have a ZMO energy. And then as you increase the magnetic field, spin up and the spin down states would have different energy. And then if you shine a pulse of light onto the spin, if the energy of the light pulse matches the energy difference of the spin up and spin down states, then the photon can be absorbed by the spin, and then the spin can be flipped. As a result, you can have absorption in the spectrum, and the frequency of the absorption would be equal to the G factor times the mu becomes the magnetic field. So from this measurement, what we can learn is we can learn information about the G factor. Why is that important? The G factor will tell you a lot about the spin environment. For example, if the spin is anisotropy, for example, if it's Ising-like, then we can measure anisotropy in the G factor. For this situation, G factor wouldn't be isotropic number, it will be a tensor, so have different values in different directions. And this is how we measure the Terahertz ESR. In the Terahertz spectroscopy, we apply a magnetic field along the light propagation direction. And if you think about it, if you apply a magnetic field along this direction, then the spin would process this way. So naturally, the spins would absorb, if the energy of the photon is right, the spins would naturally absorb a circular polarized light. And then if you flip the direction of the magnetic field, then the spins precess in the other direction, so it would absorb a different handedness of the circular polarized light. So we measure the signal with the field in the +7 Tesla and the -7 Tesla. So we flip the field direction, and if we look at the difference, then you will see a nice ring of the signal that's due to the ESR of the spin system. So this is our data in the frequency spectrum, and you can see the Terahertz really provides some very nice data in this high field and high frequency range. Although traditionally ESR data is measured by microwave cavity measurement, but as you can see, they provide really limited frequency range. And when we put on our Terahertz data, we increase the accuracy of the obtained G factor by at least 1 order of magnitude. And from our measurement combined with this low field microwave measurement, we get a very good idea of the G factor. It's very close to the free electron G factor, which is 2, and it doesn't show any anisotropy. So you can see the spins in this system really behaves like a Heisenberg-like spin 1/2 particle. And as a result, this valence bound state is a really accurate description of the system. So I just told you about some stuff we have done about more like 2-dimensional materials. So what if we bring frustration into 3-dimensional? So I showed you that 2-dimensional, the basic geometrical shape that involves geometric frustration is a triangle. For 3-dimension, if you look at then basic geometrical shape is a tetrahedron, because this is the simplest 3-dimensional structure you can make out of triangles. And there is a group of material that has this particular shape and the chemical structure that's called a pyrocross. So on the A side, there is usually the rear earth ion that carries magnetic moment. On B side, there is usually a transition metal. And then this forms the structure here. Basically, A sides and B sides are interpenetrating parallel lattices, which can be shown here. So each side, if we look at A side only, then it is formed by the structure of corner sharing tetrahedron. And there are materials that show this interesting structure, for example, holmium titanate and dispersion titanate. And for those materials, those 2 materials show the rear earth ions. They are very classical objects because the spins are very big. And they are very anisotropy. The crystal field in this material limits the spins to point either into the tetrahedron or out of the tetrahedron. So it's really a 2-state for the spin, and the effective interaction between the spins are anti-ferromagnetic. So as a result, the ground state of this single tetrahedra would have this so-called 2-in and 2-out configuration. So there will be 2 spins, one to point into the center, and 2 spins, one to point out of the center. But since there are 4 spins on this tetrahedra, there is also a huge amount of possibilities these 2-in, 2-out can be realized. It turns out for a single tetrahedra, there are 6 different possibilities of this 2-in, 2-out state. As a result, there is also a huge number of degenerate ground states. And by the way, those type of material are called classical spin ice, and the reason they get named spin ice is because the 2-in, 2-out state is similar to the proton disorder situation in water ice. This is where they get this name. And because there is a huge number of degenerate ground states, if you go down in temperature, the entropy wouldn't be able to completely be released as you cool down to low temperature. If we look at a single spin, then because it can point into or out of the tetrahedra, then there are 2 possibilities at high temperature. So you would expect the entropy to be proportional to logarithm of 2 times the number of spins in this system. And then when we go down in temperature and then you integrate the heat capacity peak, you would be able to measure how much entropy is released as you go down in temperature. And it turns out there's a huge amount of entropy not released, even if you cool down to very low temperature. And this is a classical sign of the existence of this huge degenerate ground state. And this puts spin ice material as a classical spin liquid in the sense it has this huge ground state degeneracy, but because of the large spin, the dynamics of this material at low temperature is not controlled by quantum mechanics, but instead by thermal fluctuation. And later people realized that when you have this so-called ice rules to enforce 2-in, 2-out structure, and if you flip a single spin out of the ground state, for example, if we flip this spin here, then for this one you have 3 out and 1 in. But for this one you have 3 spins pointing in and 1 spin point out. So effectively for those 2 tetrahedras, the magnetic charge on the tetrahedra is unbalanced. And the result is the same as creating a pair of magnetic monopole and anti-monopoles in those 2 neighboring tetrahedra. And this is an interesting realization of novel particles cannot be found anywhere else, but can be realized in a condensed matter system. So to put a recap for classical spin ice materials, there's a huge number of degenerate ground states that all follow these 2-in and 2-out rules, and the excitation out of the ground state is these magnetic monopoles. But there is an energy gap between them. So and also the energy barrier between those different states are big. As a result, the dynamics of those materials at low temperature is completely governed by thermal activation. So we want to study quantum spin liquid, but the classical spin ice material is a classical spin liquid. So people were thinking, what happens when we bring in quantum fluctuation? And there are several ways of doing that. If you look at the Hamiltonian, this Hamiltonian describes what happens with classical spin ice because there is only this JZZ term. But if you include interactions among the transverse components, then you bring in quantum fluctuations between the spins. And as a result, it is possible to realize a quantum spin liquid because now the ground state, due to the quantum fluctuation, can be a highly entangled state. And it is possible to have a quantum spin liquid in this case. So we realized that the material ytterbium titanate is an interesting candidate for the quantum spin ice material. If we look at the inverse susceptibility, then at high temperature in the paramagnetic, it follows the Curie-Weiss law, and by looking at behavior at high temperature, you can define a Curie-Weiss temperature. And then as you go down in temperature, most material will eventually order, so there is a neo temperature. And below this temperature, people call it spin solid because there is long-range order. And but interesting thing happens between the boiling temperature and this Curie-Weiss temperature, which usually tells you how strong the spins are interacting. And here is usually where the spin-liquid physics would apply. And if you look at the heat capacity of the ytterbium titanate material, which is shown in the black curve here, you see a very broad bound at around 2 to 3 K. And below about 300 millikelvin, you see a very sharp peak. And this peak indicates the possibility of a long-range order, but this very wide bound actually tells us that the spin-spin correlation starts to develop around this temperature. So actually, at temperatures higher than this peak and around this bound, we have a correlated spin situation, so where we might find spin liquid. But in order to look at this material, we want to know exactly what those interaction parameters are. And if you think about these spin systems, then you realize if you put a strong enough magnetic field on this frustrated spin system, when the field is strong enough, you can polarize all the spins to point in the same direction. As a result, you can have a field-induced ferromagnetic state. And so, if we assume those interaction parameters does not change as a function of field, then in the ferromagnetic states, we can look at the spin wave dispersion. As a result, you can learn something about these interaction parameters. And this is what people have done with neutron scattering, shown here. And here is the data, this dispersion of the spin waves they collected at 5 Tesla and 2 Tesla. So these are in the field-induced order state. So you have well-defined spin wave dispersion. They collected the full spectrum of these spin waves, and they also did the theoretical fitting to those spin waves. As a result from the fitting, one is able to obtain the spin interaction parameters. The full Hamiltonian can be extracted, and this is the parameters obtained by fitting to the experiment data. So this panel and this panel are the experiment data, and this panel and this panel is the fitting from those parameters. You can see they agree very well. And the strongest term is still the JZZ term, and we have non-zero transverse terms. As a result, this material is really a very good realization of the quantum spin lines idea. And also, if we look at the number at the value of JZZ, it's about 0.04 terahertz, and in numbers of temperature, it's about 2K. So this tells us using terahertz to study this material is a very good idea. And this is what we did. And about quantum spin liquid, I have told you about many of its properties. For example, it's not a product state, it's not a symmetry breaking transition, and there's no traditional long-range order, and there's no classical analog. But all of these are trying to define a quantum spin liquid by what it is not. So how do we define this by what it is? And is there any signature that we can use to identify these states, if you will, a smoking gun test? So it turns out the answer lies in the type of excitations for this material. So particularly for quantum spin ice material, which is a possible realization of quantum spin liquid, there is a theoretical proposal that says for this material, if you apply a weak symmetry breaking magnetic field along the 001 direction, then the elementary excitation in this material takes the form of quantum strings that connects a pair of magnetic monopole and a magnetic anti-monopole. The key information here is the material needs to be a quantum spin ice. 2, the field needs to be weak enough, but not too weak. So the reasons that we want a weak field is that we don't polarize all the spins, so it becomes a ferromagnet. Then we will just have a spin wave. So they actually did some calculation to show that in weak field, they're supposed to be also defined spectrums of these corner strings, you can see there are overlapping groups of different spectrums. Actually, those different groups correspond to corner strings of different lengths. So here I showed you a corner string with length 3. So you will need to flip 3 spin to get this corner string, and then it's possible for corner strings to have different lengths, and they would show up in the neutral scattering as different groups of this type of excitation. And this is what we are going to look for in this material using time-domain current spectroscopy. So we did some data look at the transmission as a function of magnetic field at low temperature. And if you look at this zero field data compared with the data taken 3.5 Tesla and also the data taken 7 Tesla, there's obviously some changes happening. So we are pretty happy. We see some field dependence, and there are a couple of dips in the spectrum. We see, well, maybe we're seeing some strings. But obviously we need to look closer to make sure whether or not there are strings. And then we realize that when we apply magnetic field, as I mentioned, the spins would be precessing, and then as a result, it would have preferential absorption for circular polarized light. So we would have circular effect. As a result, if we send in a linearly polarized light, the transmitted light would be elliptically polarized. So we need to measure, in order to get a full information, we need to not only measure the transmission along this direction, we also need to measure the transmission in the perpendicular direction. This is what we did for the red curve, is transmission in the perpendicular direction. And if we look at this, you see the data is quite complicated. We have peaks and dips, although they are well corresponding in terms of frequency, but it's a very complicated or rich spectrum. And we were scratching our head for a while trying to understand what this means, until we realized that well, another thing I should say is these two spectrums, the parallel and perpendicular polarization, is measured at the same time simultaneously. We developed an interesting technique at Johns Hopkins called Polarization Modulation, polarimeter. And here we spin a polarizer and feed the signal into a logging at twice the spinning frequency of this polarizer. As a result, we are able to measure the two perpendicular channels of the transmission at the same time. This gives us another dimension of information, which would be useful. And as I was saying earlier, if we apply a magnetic field along this direction, then the spins would be precessing around the magnetic field, more or less. As a result, you would expect absorption in one of the circular channels. So this tells us it's really not right to look at this absorption in linear frames. For example, we shouldn't look at in Cartesian laboratory frame, but it would be much better to look at the spectrum in circular frame. And because we do time domain measurement, the data we obtain are all phase sensitive. As a result, we are able to perform this transformation of basis. So this is the same data set as this one, but now it's plotted in circular frame. So here I show the transmission in the right circular polarized channel and also the left circular polarized channel. And you can see right now the data is much easier to understand and much cleaner. So if we look at the data as a function of frequency and magnetic field at low temperature, we can generate these two plots. Here I show you the transmission in the right circular polarized channel and the left circular polarized channel here. The quantity being plotted is the transmission amplitude. So the brighter color means higher transmission, and the darker color means lower transmission. So wherever we have a dark line across the figure, there is a channel of magnetic absorption. So remember, at high field, we would have this polarized state of, long-range, field-induced long-range order state. So at high field, you would expect this absorption to be of the spin wave nature. But at low field, we are supposed to see these signatures of corner strings. And the first feature we realized that we see two groups of excitations. This group with about the same slope, and the slope in this figure is the same as effective G factor. And also we see another group with a higher effective G factor. And another interesting thing about this spectrum is here we see absorption from both right circular polarized channel as well as left circular polarized channel. If you think about it, it's not very straightforward, because if you point magnetic field in a given direction, then spin will precess around this field, and you're really not supposed to get absorption in both circular polarized channels. But here we see them, so it's quite interesting. And another interesting feature we see is that if you look at this region and this region, you'll see the transmission is higher in this region compared with this region. So this we call it a field-induced transparency, which means as we apply magnetic field, the transmission in the low frequency range is actually enhanced. And this also appears in the left circular polarized channel. And as temperature increases, all those features disappear. So this shows you the field-induced transparency in different plots, comparing the transmission at zero field and at 7 Tesla. We can see at low frequency range, as we increase the magnetic field, the transmission increases dramatically. So we believe this is a signature of the existence of some kind of magnetic absorption in the low field region. Although it's not very clear what it is, but it's quite interesting. And we also did measurements in a different geometry just to get more information. Here we flipped the direction of magnetic field to be in the sample plane. And when the field is in the sample plane, like this, the light travels in this direction, then the spin will precess in this direction. So as a result, you don't really expect it to have absorption in a circular channel. But instead, you expect the material to have absorption in a linear channel. So here we have TXX and TYY. So here I showed you data we measured in TXX at 1.65 K. And you can see we have two magnetic absorption channels we label C2 and C4. And this higher energy, higher G factor channel can be traced back to a field as low as 0.6 Tesla. This is quite interesting. We also measure the TYY at 4K. And you can see we also detect the two channels of magnetic absorption. We label C1 and C2. But those two channels have the same G factor because they are parallel. So if we plot all the measured resonance frequencies as a function of magnetic field together, we see a whole bunch of magnetic modes, and we label these by B means they are measured in the Faraday geometry, and C means they are measured in the Boyer geometry. And our collaborators did some spin wave calculation. It turns out these lower energy and lower G factor modes all belong to spin waves. And it is interesting that we see both a right circular polarized channel and also a left circular polarized channel. As I mentioned, when field points to a given direction, you really expect to have absorption in one of the circular channels. And why that happens? Actually, it turns out spin wave calculation can answer this question quite nicely. The ytterbium iron turns out it has an easy plane anisotropy instead of Heisenberg type of behavior. As a result, the spin is not fully polarized by the magnetic field in the same direction. So as a result, you have the equilibrium position of the spin slightly tilted away from field direction. So when the spins precess around this equilibrium position, if you look around the field direction, the motion instead of circular is elliptical. So if you have an elliptical motion, then it is a superposition of both a right-hand component and a left circular component. As a result, for this particular spin wave mode, it turns out the right circular polarized components all cancel out. They are all out of phase, and leaving us with only a weak left circular component. So spin wave calculation explains this feature nicely, and the fitting you can see it agrees with the experiment quite nicely. And also, the spin wave calculation can generate especially as the high field region can generate a dispersion relation, as I already showed you. This is the dispersion in the momentum space. This plots the energy of the spin wave excitation, and this is the momentum. And if you look at the spin wave dispersion, you can see, particularly for this mode we label N2, the dispersion is really flat. And whenever you have a flat dispersion, you can expect this mode can have a two-particle continuum that has a pretty well-defined energy. And if we look at our data closely, this is indeed what we see. This branch we label B6 has exactly twice the energy of this branch we label C2. And C2 corresponds to this M2 mode. So it's a very flat spin wave mode, which has a well-defined two-magnum continuum. So this is a two-particle continuum of a single spin wave. And from the spin wave calculation, it is also possible to generate a two-magnum continuum boundary. And here I showed you from the spin wave calculation the energy of the two-magnum continuum from this mode, which you can see agrees with the data really well. And because this mode here has the same slope of this mode, we should understand this as also some kind of two-magnum process. And another thing about this two-magnum behavior is it is possible that those two-magnum behavior is related to a quantum string with two string fits at the low field value. And here we remember that we set up to look for signatures of quantum strings in this material. And so now let's take a look at our data, see if there's any signatures at all of the existence of these quantum strings. So we can see that in the high field region, the spin wave calculation can describe our data quite well. But as we go to lower and lower field, discrepancies starts to appear, for example, here, and also there's obvious change of slope here. This tells us that in the low field region, the spin wave theory does not describe the data at all. And especially if you look at the mode C4, it widens significantly as the field decreases. And also we see this interesting anomalous magnetic absorption in low field region. And we believe all those signatures, the changing slope, the widening of this peak, and also the existence of magnetic absorption at low field region, they are all signatures of the existence of quantum strings in the material, especially in the low field regions. Because if you look at the theory, when the field is low, you are expected to have overlapping bands of strings with different lengths. As a result, it is possible that here we would expect to see this quite broad magnetic absorption, which goes away as you apply a strong magnetic. So here we set up to find the definition of quantum spin liquid material to see a defining signature. And here, using thermometric spectroscopy, we find possible signatures of existence of these quantum strings, which is a unique excitation of these quantum spin ice, which belongs to the quantum spin liquid materials group. And this we believe is a big step forward. And but on the other hand, this needs to be confirmed on studies of similar materials. For example, there are a huge amount of materials that's supposed to be possible candidates of quantum spin ice. So here I would just like to show you this picture. The study of quantum spin liquid and quantum spin ice has been involved with a lot of different experiments, for example, neutron scattering, NMR, MUSR, and thermodynamic measurements. Here we'd like to think Terahertz spectroscopy contributes uniquely and brings us very useful information of the study of quantum spin systems. And with that, I bring you my conclusions, and thank you for your attention.
Do we have questions?
Yes. So for these classical spin ice materials, only on the dispersion tightly. So in principle, there's large spins of dipole interactions are important. So this Pauling entropy is recovered at low temperatures. Correct. So this nearest neighbor icing model that you're using for the classical spin ice is not really valid for those materials.
For classical spin,
Yeah.
although the spin is large and the interaction is mainly dipole, it turns out people have done some simulation that the induced neighbor mode actually describe it quite well. It generates a lot of features, for example, the pinch points feature, the neutron scattering data, and the dipole type spin-spin correlation. So they have shown it actually describe the physics quite well.
But you need this dipole-dipole interaction.
To get this long-range spin-spin correlation. Yes, that is true.
Could you go back to the molybdenum clusters that you had earlier on? So they were triangular in shape, right? And you had an odd number of electrons to give you the spin 1/2 on a cluster. Is that right?
That's right.
So in addition to the spin degeneracy, wouldn't you have an orbital degeneracy because of an odd number of electrons in a triangular structure? The triangle C3b supports twofold degeneracies.
Well, I should say this spin is not localized on a particular ion. Instead, it's shared by this.
I understand, it's a cluster.
Yes.
I understand, right. So if you look at a triangular molecule with an odd number of electrons, you can have twofold orbital degeneracy just by virtue of the symmetry.
Okay.
And so my question is, why doesn't it distort? It should spontaneously distort. The triangle should be unstable.
Right. About that, they have done careful structure analysis, and they didn't find any evidence of distortion or structure change down to the very low temperature. And another thing is, these chemists believe by using this cluster method, you can avoid, to the first order, you can avoid this Young-Taylor effect, so distortion should be minimized.
How do you avoid the Untitled effect?
That detail I'm not very clear about.
That's exactly what I was alluding to when you have.
Yeah, that I think best to be answered by those material scientists.
Just a follow-up on the spin ice. So the spin ice rules themselves, 3 in, 1 out, and so on. They're classic, right? They're purely classical. You know?
Yes.
And so, again, so people apply them usually to large spin systems, right? Just only to hit it without any dipole long-range interactions, just with one detector.
Yeah.
The spin ice rules themselves are classical. So when you talk about quantum spin ice,
If you look at this one, you can write it as like J times the total magnetic moment squared of particular dimension. That implies the spin ice. But for quantum spin ice, the important thing is this particular term is still the strongest term in Hamiltonian. So all the other transverse terms are perturbations. So the spin ice correlation still exists, and that is partly realized in the turbine titanium material. The JZZ term is still the strongest, but also there is one term about the same order.
Right. So it's still almost classical, right?
No, because the spin is quasi-spin 1/2 of J. So the quantum.
Right. So the JCC is the strongest. Right? This one.
Yes.
Yeah.
JZZ is the strongest.
Okay. I missed something. You mentioned something when you do some spin polarizing experiment, you double the frequency or something. I missed that particular part. It's when you have some frequency doubling somewhere.
Actually, I didn't mention frequency doubling, but some of the experiments we see signatures of two modes of excitation. One group has about twice the energy of the other group. So this is basically magnon, which corresponds to a single spin flip. So this group of the two magnon nature, which corresponds to two spin flips.
You may have been referring to the LiDong measurement.
Oh, okay.
Right.
So that's where Yeah, here.
Somewhere around here, right?
So this is Terahertz polarimeter. We call it polarization modulation. So here we have a polarizer, which is a Terahertz polarizer, just a wide grid polarizer, and then we spin it at a high frequency. And because polarizer does not distinguish 0 and 180 degrees, so naturally this polarizer will have a 2 omega component. So if you write down the Jones matrices for this type of line path, then you here I should say before the detector we have another polarizer. So you can see we have this vector describing the electric field of the Terahertz pulse here, and then this is the matrices describing this rotating polarizer, and then we have another polarizer, and then if you do the math, then you can see this rotating polarizer can be written by this, and looking at this, you realize there's a 2 omega component, twice the angle position component here, and then final result is this. So we feed the signal into a locking, and then we locking at twice the frequency here. So the 2 channels measure EY and EX separately. This is how we do the Terahertz polarimeter experiment.
Thank you.
Just a question of this 2D spin cluster material. What was the RVB ground state that you were proposing? Because it looked like it was not on a, it's on a triangular, effectively a triangular lattice, except for, but they're not resonating on the triangular lattice?
Right. For that, because below 100K, effectively 2/3 of the spin seems to disappear, so they believe those 2/3 of the spin condense into a resonant state. But however, 1/3 of the spin is still in a paramagnetic state. So it's a coexistence of this resonance valence bound state. And so this spin, for example, would be in a paramagnetic state, but here there would be, the neighboring spins would be a valence bound state. But this structure is not static, it's believed to be dynamic. So as a result, they think it's still a quantum spin liquid state.
But the valence bonds only live on the honeycomb lattice, or they live, or they get?
Yes, yes, that's what we believe is happening. So this center spin, for example, here is still in a paramagnetic state.
So I guess so on a triangular lattice with short-range valence bonds, you expect to have a gap spin liquid. But when you go to a bipartite lattice like the honeycomb, if they're short-range valence bonds, you actually don't expect spin liquid. It's like bipartite versus non-bipartite lattices.
Right, but actually, this is just a simplified picture, and this structure is by no means static. So I don't think it has this like honeycomb.
Oh, okay. So it's not actually breaking the symmetry.
Right, exactly. So they measure the structure carefully. If it's a static configuration, then you expect the breaking or lowering of the lattice symmetry. And this was not seen from any of the measurements.
Okay, any others? If not, let's thank LiDong again.